Bridges can be small and simple to big and meticulously engineered. Structural engineers have designed different kinds of bridges throughout the centuries, and they all serve the same purpose. They allow people to get from point A to point B. The stability of a bridge is contingent on the balance of three main forces: tension, compression, and load. When this balance is achieved, it stays locked in place. While bridges may be designed top-down, they're built from the ground up. Construction starts with the bridge's foundations. This usually consists of a set of piles, allowing the forces transmitted through the bridge to be evenly distributed to the ground below. A tier above, there's the substructure. This is usually comprised of abutments at the bridge's ends and piers right above the bridge's piles. Then we have the superstructure, consisting of the deck and other structures in place to help tie the whole bridge together. These fundamental traits allow bridges to function effectively, regardless of their design. So why do bridges come in so many different shapes and sizes? Well, different situations call for different types of bridges. Arch bridges have been built for millennia, and for good reason. For one, they're relatively cheap and easy to construct. They've historically been made from natural materials such as stone and brick, and yet they're incredibly strong. Their iconic arch evenly disperses the load across instead of down. The load is then transferred to the base of the arch, which functions as a strong pair of abutments. Nowadays, materials like steel and pre-stressed concrete make it possible to build longer arch bridges. They can even be built over deep gorges, such as the New River Gorge, where the roadway is 876 feet high and 3,030 feet long. Beam bridges feature an even simpler design. Fundamentally, beam bridges consist of horizontal beams supported by a series of piers. Their strength mostly depends on the distance between each pier, so they rarely have individual spans of more than 250 feet across. However, some beam bridges are far longer than this, such as the U-beam bridge. This bridge has 482 spans, totaling 0.75 miles in length. It was originally constructed entirely of teakwood and was the longest teakwood bridge in the world. Truss bridges can be thought of as slightly more sophisticated beam bridges. They feature a series of triangular-shaped supports in between the horizontal beam and the piers. This allows them to handle a high load over large distances. Due to the simplicity of their design, some truss bridges can even be assembled on-site with prefabricated parts by a team with no special equipment, such as the Bailey Bridge. The first cantilever bridge, which was built in 1867, was seen as a major breakthrough. It works by using cantilevers, which are horizontal structures supported only on one end. It sounds a little dangerous, right? But it's actually extremely safe and secure. If a gap is too wide to be spanned by one cantilever on each side, a beam or truss bridge is often placed between the arms of the two cantilevers, connecting them into one suspended span bridge. One big advantage cantilevers have over other bridge types is in the efficiency of their construction. They don't need temporary structures to support their foundation. An iconic example of this is the Golden Gate Bridge. Suspension bridges are used for long crossings with lengths spanning up to 7,000 feet. They're also used in places where there isn't a stable enough foundation for arch bridges. In suspension bridges, the piers on the north and south end are connected by draping main cables, which are attached to the deck by vertical suspender cables. The towers act as a substructure, and they resist the forces that are applied to the main cables. Suspension bridges are relatively light and flexible. They may sway and ripple with the wind or move when the ground shakes, both vertically and laterally. The challenge is to assure aerodynamic stability and minimize motion. Cable-stayed bridges also rely on cables to suspend the deck. but all of the nearly straight diagonal cables attach directly to the towers. The towers transfer the forces from the cables to the foundation through vertical compression. As seen in the Millau Viaduct, these cables meet at the midpoint of two towers. Fewer towers are required to be constructed for this type of bridge than for a suspension bridge of the same length, since the towers can be further apart from each other. The superstructure and substructure are rigidly connected as a single unit. This can be handy for specific design requirements, such as a seemingly steep incline in the case of the Ishima-Ohashi Bridge. In reality, it has a mere 6.1% gradient on one side and a 5.1% gradient on the other. Lastly, there are movable bridges like the Tower Bridge. It features a drawbridge at its midpoint, allowing ships to pass through underneath. The two parts of the lower deck are counterbalanced by two movable sections weighing over 1,000 tons each. It's also a great example of a hybrid bridge, since it's also a suspension bridge. All the different types of bridges show just how complex these structures can be, and yet the possibilities are endless. There's a bridge for every terrain, every unique purpose. They are truly a remarkable feat of engineering.